Streaming has started, is it not, Professor Yogarajan?
Just sir, that you have to tell. Yes, we are live. Professor,
Okay.
now you can start.
Yeah. Okay. Good evening. So, over the last 3 sessions, whatever we have discussed, and if you have internalized some of those arguments,
Yes, we are live.
today I'm expecting that we will get a
Sir?
complete. Yes.
Sir, your voice is feeble, sir.
Let me see if. How is it now? Is it better now?
For me, it is very nice, Professor, but students will have to tell.
Syed, is it okay?
Sir, no, sir.
Yes,
Same voice.
sir, I can read, sir.
Okay, then I think Syed, you have to see whether you have to increase the volume of your device.
Oh, okay, sir.
Okay, so I think what we will see today is there are 3 important things, and if you understand these 3 important things, then I think you will be in a good position to appreciate quantum mechanics. One is quantum. So to start with, we have something called a quantum system, and then you have to understand with respect to this quantum system, what is the quantum state? How do we describe quantum state of a system? Okay. Second, time evolution. Time evolution of the state. And third is measurement of properties. Of properties. Okay, so if you understand these 3 things, more or less you get the basics of quantum mechanics correct. Okay, so from whatever we have discussed so far, we will try to heuristically develop arguments so that we can understand these things. Okay, so that is the aim. So this is slightly unconventional way of doing this, because quantum mechanics always starts with postulates, and postulates will tell you what these things are. I am trying to present certain experiments from which I am attempting to discover what is the best way to describe each one of this. So first, I would like to talk about quantum state. And this is very important because this quantum state is something which is very different from classical state. Okay, that is why this is a complicated concept, and also a lot of kind of whatever mystery that is created around the concepts in quantum mechanics is involved in proper understanding of quantum state. So what
Professor Sathyanarayana, your mic, some connection little problem, some sounds are coming in between. Mic can be just connected once again.
is it okay now? I have actually plugged. plugged in again.
Okay. Okay.
Is that sound coming still?
Still, yes. Is it not? Professor Yogarajan?
Professor, sound comes not through mic, through your connection. You may unplug and again replug.
That's what I did now. Okay, so I did it. So is there a
now there is no noise, Professor.
okay? So we will first talk about quantum state. Now, maybe it is instructive to talk about classical state first, but let's not worry about classical state. We have discussed some experiments in the last few classes. So we will try to understand how do we describe a quantum state is. See, one of the experiments that we discussed is the polarization experiment. So I have a source, and then this is emitting polarization, photons in this polarization. And then I have a polarizer put in this direction. And through experiments, I realized that after this, whatever comes out is a polarization in this direction. Okay, how do I know this? I know this because if I put another polarizer, all the photons that come out of this one will also go out of this one. And what about those photons that don't come out? So the photons that are coming out like this, and the photons that don't come out are like this. This is what we have discussed earlier. From this, if this angle is theta, and if I call this as probability of transmission and probability of absorption, if this angle is theta, from the behavior of large number of photons and its comparison to classical behavior, we can conclude that the probability of transmission is cos theta, and basically cos square theta, and probability of absorption is sin square theta. Okay. Now, if you consider this experiment alone, and you can ask a question, what should be this state? Okay, so we are what is the question that we are asking? So what is the state? What is the polarization state? Polarization state at this point. So if you, I think we call this as P1, before P1. Okay, suppose nobody tells you what this state is, you do not know what is this state, right? So there is some source about which you don't know that is in which direction it is polarized. So you don't know this state. But after using this photons and doing an experiment like this, you realize that this state, if I call this state as, so let me say that this state is some kind of an alpha, then from the experimental experience that I have, I am going to say that this contains this one, plus it's a combination of this one and this one, and this combination has to be a linear combination. And what is that we write? We write some cos theta here and sin theta here. If I write like this, these cos theta and sin theta, they are called probability amplitudes. Basically, they are probability amplitudes, and they are actually complex numbers. In general, they are complex numbers. Probability amplitudes, and they are complex numbers. Now, what are these things? Okay, so these things, in general, in general, so basically this is one state. So for example, if you forget about this and then ask what is the state after P2? What is the state after P2? So if you ask that question, then you know for sure that it is this. So that means this is also a state. This is also a state of the photon. And this is basically a combination of these two states. This is basically a combination of these two states. Now, such combination is a legal and perfectly valid description of state in quantum mechanics. Okay, so this is something which is quite new and unprecedented, because you remember there is something called a cat paradox, which Schrodinger had discussed in as early as 1935 or 36. So you may remember this cat paradox. You might have read this in popular books. Okay, so cat paradox. What this paradox simply tells you is that you have a box in which you have a cat. Okay, so you put a cat, and then you put an arrangement where you have some some kind of a cyanide gas in a bottle, and then let's say that you have a hammer. Okay, and then you have some kind of a radioactive material here. Let's say this is some radium which emits alpha rays, and if an alpha ray is emitted, this hammer will break this glass jar, and cyanide gas will come, and then the cat will die. Now, if this did not emit alpha ray, then this hammer will not break the gas and cat is alive. Now, you seal this box in such a way that there is no information about what is going on in this box. Now, if you look at the radioactive decay is a probabilistic event. You don't know when the next alpha ray will decay. Maybe if you wait for 1 hour, there is some probability that alpha ray might have been decayed. Okay, so alpha ray might have been decayed. If it has decayed, then the cat would be dead. If it did not decay, then the cat would be alive. So it is like this case, right? So we do not know until we see whether this photon is going to be transmitted at P1 or it is going to be absorbed at P1. So if you ask a question, what is the polarization state before P1? We say that both possibilities are there. In the same way, we do not know whether the cat is alive or dead, but if you open the box and look at it, then you will know. That is like putting a polarizer P1 and then knowing it has transmitted or not. So unless you do a measurement, you will not know whether the cat is dead or alive. So when you don't do a measurement and you ask what is the state, you must say so if you say that I have a cat as the state, then this has to be some probability P times it is alive, and some other probability. Okay, I must probably say this is some C1 times cat alive plus some C2 times cat dead. Okay, so this is how I would write this state, where probability that cat is alive is equal to modulus C1 square, and probability that cat is dead is equal to modulus C2 square. And of course, modulus C1 square plus modulus C2 square is equal to 1. That means only one of these two things will happen when you measure. Okay, so this is what this paradox is. So one doesn't understand what this means. So what is the meaning of this? That means, is it dead and alive, or it is neither dead nor alive? So it looks more paradoxical because we are now subjecting a living creature to this description. But if you so it is very important to understand how to interpret these things, and these interpretational issues are very, very important and very very complicated also. So what I wanted to point out at this point, at this juncture, is that the description of a quantum state has got certain implications, like this Schrodinger cat story, that you need to understand this properly. Okay, so now I would like to so first thing that I would like to say is that the from actually, as far as polarization degree of freedom is concerned, there is no difference between classical polarization and quantum mechanical picture of that, because classical polarization also so for example, polarization states of an electromagnetic wave, okay, form a complex two-dimensional vector space. Okay, that means if you define a vector space V such that this is alpha and beta, such that alpha and beta are in complex numbers. Okay, alpha and beta are in complex numbers, and of course, so you have, so this kind of this is a complex two-dimensional vector space. Now every element, okay, so every such vector describes some polarization state, and this is what we call as a Jones vector. That means, what do we understand from this situation is that,
Sir?
yeah.
So modulus alpha square plus modulus beta square equals to 1, that should be mentioned or not, sir?
Yeah, I think we should mention that. That is modulus alpha square plus modulus beta square is equal to 1. Okay, so unit modulus is important. So now it means that, what does that mean? That means this kind of a state is some complex number like this, a complex vector like this. This is some complex vector like this, and this is some complex vector like this, and so on. So from this we understand that the state is a vector. Okay, is a vector. Now this is a preliminary understanding, but we can say that state is a vector, and this vector in this particular case it is just a two-dimensional vector, complex vector. So state is a, in fact you can say, is a complex vector. That means a vector with the components that are complex numbers. That's what it means. So state is a complex vector. Okay, it is not a, so what I'm saying is we are trying to look at this from the polarization degree of freedom, but then whatever I am drawing this conclusion is actually a very general conclusion. Every state is a complex vector, whatever is your system. Okay, so now we can say that this is like the state of a quantum system. The state of a quantum system is a complex vector. Okay, and normally I'm going to little bit modify this statement. When you have a vector, okay, suppose I have a vector like this. Let's say I have a vector like this, even three-dimensional normal vectors that we are familiar. Now you can say that there is a unit vector. Let's say this is a unit vector. Okay, let's say I cap. Now any multiple times I cap, alpha times I cap, for some alpha, okay, let's say to start with some real number alpha, is also another vector, right? Alpha times I cap is another vector. So maybe if alpha is greater than 1, so let's say if this is I cap, this is alpha times I cap. Okay. Now you can say that this entire, so this is for every value of alpha, what do you get? That is, if you are considering, let's say V1, which is set of alpha times I cap, such that alpha is in real numbers, you will have infinitely many such vectors, right? Suppose alpha is negative, then you may have a vector like this, and so on. So that means you are getting all points on this straight line as members of these vectors. You put any point here, start from the origin, you draw a line, that is one vector. That will correspond to one of the alpha. Now every vector in this space can be obtained from I by just multiplying with a real number. What does that mean? That means once you know I, every other vector is linearly dependent on I. So that means the number of linearly independent vectors here is only 1. So what happens? This is a vector space. Okay, so this is a vector space. Okay, what is the dimension of this vector space?
So one
dimension. So this is a one-dimensional vector space. Okay, so that means if if I have my quantum state, if I have the state to be any vector in this space, okay, it may be alpha I or beta I, whatever. So if it may be any vector in this space, okay, but then all this space, this entire space, can be characterized by one vector, namely I cap. What is the significance of I cap? Now this I cap is a unit vector. What does that mean? Why do we call it a unit vector? Because your I cap vector has got the magnitude 1, a unit norm. Okay. Any other vector will not have unit norm. That is why we call it as a unit vector, right? So unit vector is having this norm is equal to 1. Okay. So now what is it that we are going to modify this statement is that, so in general, I am now going to write the state of a quantum system is a vector space. In general, it is a vector space. Okay. In general, it is a vector space. So maybe let me write that. In general, a vector space characterized by a unit vector. By a unit vector. Okay, so I want you to think about this. I do not know if you have thought about this, but this is something which is very useful. Now we have a complete vector space, but we will be interested in unit vector. Okay, so what is the complex vector that I am talking about here? I'm going to talk about complex vector, which is a unit vector. That is the space, or that is the vector that I'm going to use. Okay, so this is, so you may say that, okay, I have some. So let us say,
Sir?
Yes.
Sir, the state of a quantum system is an element in a vector space or is a vector space?
So what I'm saying is, it is any element in this vector space will qualify to be a state. But
Okay,
then once we know the unit vector, then all
Yes.
other things can be obtained from that, right?
Yes, sir. By a scalar multiple of.
By a scalar multiple of that.
Yes, sir.
So this unit vector is basically what represents this entire vector space.
Okay, sir.
Okay. And basically, what is unit vector? So let me probably translate it into some familiar language. Suppose, so let us agree that we will denote a vector. Okay, so denote vector by a ket. Okay, so right now you just treat this as a notation. So let's say I have a vertical line like this, and then let's say I have some alpha, and then an angular bracket, right angular bracket like this. This is called a ket. Okay, this is just a notation. Okay, so right now, please understand that this is just like a rotation. And that is why sometimes earlier you might have seen that I would have written this polarization up down in a ket like this. So denote a vector by a ket. Okay, now if it is a unit vector, then what is that I should have? Okay, so when you take, suppose I have a ket vector like this, and if you want in the matrix language, so in matrix language, you may say that this ket is like a column matrix. Okay, so column matrix. So every Jones vector is like a ket. Okay, like for example, I might say that a polarization state like this. Okay, so this one is like 1, 0, and a polarization state vertical like this is 0, 1, and so on. So I can say that everything I can have some matrix representation of this state. Now what happens? I want to I want to calculate what is the norm of this vector, then I must imagine that I have a corresponding bra vector, which is written like this: vertical line to the right, angular bracket to the left. So this is called bra. And this one is basically a row matrix corresponding to that. So basically, how do I write? I will write this alpha dagger. What is this dagger? So this is basically, if you have a matrix like this, so this is a column matrix, transpose the column matrix, and then take a complex conjugate of that. So this is called an adjoint operation. So what is that? This bra will be a row matrix with complex conjugation. Transpose means the column will become row, right? So this is a row matrix. Now you know, when you multiply these two things, that is, you say alpha, 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 what you get? You get a row star into a column, correct? And this is going to be some real number, because if you think that you have components, suppose let's say you have a component A1, A2, etc. Here you are going to have A1 star, A2 star, etc. So what you get will be modulus of A1 square plus modulus of A2 square plus etc. So everything is a real number, so you get a real number. Okay, so you get a real number. And what is the norm of this vector? So norm of this vector, norm of alpha, is basically square root of this alpha alpha, correct? Square root of this alpha alpha. Now we want a unit vector. We want a unit vector. What does that mean? That means the norm should be 1, right? So that means your alpha and alpha must be equal to 1. So what are the unit vectors? So unit vectors are normalized kets. Okay, so if you normalize a ket, that you will get a unit vector, and any other member in that space will be some multiple of this alpha, right? So quantum state is basically a normalized, basically unit vector corresponding to that vector space. Okay, so this is one point I want you to appreciate. Okay, any question at this level? Now we can ask what kind of okay, so now let us go to a new situation. We have developed some understanding from this polarization thing. Now let's go to a new situation where we have a source of photons. Okay, and this is emitting photons like this. Now you have a beam splitter. Okay, so we have a beam splitter, and then you have a detector D1 here, the first experiment that we discussed in the sequence of these things. Now you have a detector D2 here. So now what we observe is that you have n photons, and D1 received n by 2 and D2 received n by 2 on an average. That is what was the observation. So what this told us? What was the conclusion that we could draw from here? What conclusion can we draw about a single photon? What happens when a single photon comes to the beam splitter? So this is basically a transmitted thing, and this is like a reflected wing. So what will happen to photon at the beam splitter? What was our discussion on this? What did we understand?
Sir, maybe it will go transmitter or reflector.
So we do not know before the photon crosses the beam splitter whether it is going to get transmitted or reflected. But after beam splitter, what happens? One of the two will happen. Either it is transmitted from the beam splitter or reflected from the beam splitter. How do we know that? How do we know that? We know that because, I mean, what was our observation? A photon is coming and we have a beam splitter. So the photon must come to this. Photon is coming to D1, and when it is coming to D1, D2 is not clicking. When it is coming to D2, D1 is not clicking. Correct? If that is the case, then we can say that it is either going to transmitted or going to reflected. Is that clear? Now, let us say that we have something called a coincident detector. Okay, so let us put another device called coincident detector. What this does is, if the photon at if D1 and D2 both are clicking, then this will both are simultaneously clicking, then coincident detector will register a count. If either D1 or D2, one of them only is clicking, then coincident detector, because coincidence by means what? They both are clicking simultaneously. So one can put a coincident detector and then check whether, now it is very easy. No, now we have, so right now what is our aim? Our aim is to understand, see wave particle duality. Okay, so let us ask a question. What happens to this wave particle duality? Okay. Now suppose if, suppose let's say we send n photons, and if it is a particle, I mean if this photon is a particle, then coincident, how many counts coincident detector will register?
Sir, can you
Sir,
ask
one.
the question once more, sir?
Zero
Okay, so,
count.
so 0 count. So you understand how coincident detector works?
So,
Coincident detector registers a click if D1 and D2 click together. D1 and D2 click together. Otherwise, coincident detector will not register anything. Okay.
So, sir,
Yeah.
As this is a single photon source, there is finite time lag between two photons emitted, and each photon either will transmit or reflect. Therefore, this coincident detector will never click.
So that is one argument. Okay. So let us say NC is the number of clicks number of clicks of coincident detector. Okay, and let's say N1 is number of clicks of D1, and N2 is the number of clicks of D2. Okay, so we know that total number of photons are N1 and so let's say total number is N, and that is N1 plus N2. Correct? That is N1 plus N2. Now you can probably write some kind of a quantity like this. Let's say NC, okay, divided by N1 plus N2, something like this. Okay. Suppose if you write something like this, so what does that mean? So let us call this as some A. Okay. Now, if wave nature is there, wave nature means what? Wave can go through both the directions simultaneously. That means every time, for every, if photon has a wave nature, the photon can actually go transmission and reflection can simultaneously take place, like eigenwaves. No, it can actually wave out in both the directions, and so D1 and D2 will click simultaneously for all photons, right? So if you think you have a wave nature, then this A should be equal to 1. Correct? Suppose if you have a particle nature, that means photon is a particle nature, then what should happen? The particle should either go to transmitted or go to reflected, because it may probability will be there. That means it may not, you may not know whether it will get transmitted or reflected, but then you know that one of them only will happen. So in that case, what I should expect? There should not be any coincident counts. That means I must have A to be equal to 0. Okay. Now this is a nice experiment where you can actually find out whether a photon. Why we should ask this question at all? Photon means I thought, okay, we will have only particle nature, because we had seen earlier that even if you have a single photon source, we have seen that it is showing interference. Interference is a wave phenomena, right? So there may be some wave nature for the photon, and in an experiment like this, what is the actual nature of photon? So if you ask that question, this experiment probably makes sense, and you should be able to find this, whether its wave nature is important or particle nature is important, or both natures are there. What is the situation? So this was, I think, in 1956 or so, people tried to do this experiment and tried to, yeah.
Sir, if we put the same coincident detector in Mach gender interferometer, sir, the result will be same with this.
So we will come to that, but let us first try to discuss this. So now, see, some of you who are doing experiments will realize that no experiment you will get a perfect 0 or perfect 1. There will be some experimental inaccuracies, right? So for example, you have to design your time windows of D1 D2 such that when a click is occurring in D1, D2 should not have a click up to some time, so that the coincident detection will not get registered. So there will be a lot of experimental challenges. I am actually not considering all of them here. I am in some sense ideal. This experiment was done basically. I'm not saying this was just a thought experiment. This experiment was done.
Like, sir, this coincident detector, how best it can result between two?
So that is very important. And assuming that all of these precautions have been taken, and so if everything is, I mean, experimentally, if there is no ambiguity, all such things are being carefully analyzed and corrected, then I think this is kind of a decisive experiment which will tell you photon is either wave or a
Sir,
particle.
is it done actually? Means
It was
people
done,
are
yes,
done.
in 1956.
Okay, sir.
So this experiment was done in 1956. I think it was done by Hansbury, Brown, and Twiss. This was kind of a PRL paper in 1956. These three guys did this experiment. Okay, so I'm a little bit curious as to what many of you think would have been the result of this experiment. Any of you have any guess? What would have been established, or from whatever you know, what do you think would have been the result?
Sometimes 0, sometimes 1.
0, sir.
Why sometimes 0, sometimes 1?
Maybe that indeterministic nature will be there. So it cannot count something between 0 to 1. Okay, no, sir. It can be a fraction also, no?
Yeah, it can be fraction, but a fraction will not be due to the nature of photon. It may be slightly more than 0 or less than 1 because of experimental indeterminacy.
Okay. I don't know,
But
sir. I think duality is there means it should not be 0 all the time.
no, I just want you to understand that, see, duality means what? Duality is so when you say like this, it gives me a feeling that you are ascribing some fishiness to the photon. Okay, so the duality of the photon does not mean that the photon has any decision making power. You follow, no?
Yes, sir.
So photon does not, so it is not fishy. It's a physical system after all. So it is going to respond to whatever it is subjected to. So what is interacting with the photon here? It is what is interacting is the beam splitter.
Beam splitter, yeah.
Okay, and we know how beam splitter works for an electromagnetic wave.
Yes.
So if photon is a wave, it should happen in the same way, correct? So if photon is a wave, and if with the beam splitter, if it shows wave nature, then we should get A is equal to 1.
Yeah.
If photon is a particle and it presents that nature to the beam splitter, then we should have A is equal to 0. So in this background, I just want you to give some thought from also, because also keeping on the mind that some of the experiments that we discussed in the last.
Sir. Okay. With beam splitter, we saw that wave phenomena is coming. So
in which experiment?
In the third experiment, we saw that one detector was registering only zero photon, and other one was having N.
Okay.
That one.
So from that you conclude that A should be 1. That means photon has a wave nature.
Okay. Yes, sir.
Okay. Good. So any other?
Sir. One thing, sir, in third experiment we have seen, if we lost the path information, then this interference happens. Sir, here suppose this coincident detector clicks, then can I say that whether it has come through by transmission or through reflection? I think no, sir.
If coincident detection clicks, we will not be able to say that, right?
yes,
Because both detectors are receiving the photon.
And this is one thing, sir. Sir, this is different from polarizer. This is a beam splitter, right? So, as you said, after passing through, the state will not collapse. It will evolve unitarily, right?
Yeah.
So, I don't know, sir. First, I feel that first place I felt that particle.
Sir, does that mean?
Yes, sir.
Sir, a photon is a wave and a particle, right? So it's a combination of both. So always you should be one, right?
Okay. So what I'm saying is that you may have some logic or some understanding of, like what Arpita has said, that she, based on her interference experience, she thinks that A should be equal to 1. So you may have some experience that, okay, I know photoelectric effect, Einstein showed that it is a particle and hence it has to be equal to 0. So you may have some argument, right? So if you have some argument, I would like to listen to that argument. And sometimes even if you don't have an argument, I think scientists generally have something called a gut feeling. What is that gut feeling? So you don't know why or what is the reason for your hunch or for your guess, but then you strongly feel from inside that this should be like that. Okay, so if you have a gut feeling, I would like to see how many of you have a gut feeling for A is equal to 1. So please raise your hands. And this gut feeling doesn't require any explanation. Okay, so don't think that I'm going to ask you.
Sir?
Yeah.
Sir, if it's wave nature, for every photon, both detectors will detect, right?
Correct. That is how you get A is equal to 1.
Sir, then it should be 1/2, right?
Why? No, coincident detection is going to, every time D1 and D2 are clicking, NC also will, coincident detector also clicks, no?
Yeah, so like NC will be equal to N1, NC will also be equal to N2.
NC will be equal to okay, so I think you have a point. Maybe I have to carefully define this. So how do I define? So let's say so A is equal to okay, so what happens if N1 is equal to N by 2? This is equal to N by 2. So this is N, and I think this is okay. See, what I'm trying to say is that so D1 and D2.
You can write just NC.
So N by 2 will come here, and every time all of them are coincident, right? So N by oh no. If it is a wave, all the N will come here and all the N will come here, right? Every photon will come to both detectors, right? Every photon will come to both the detectors.
Yes, sir.
And so NC also will be equal to N. So that is why you are saying it is
yes.
N by 2. Okay, so I think you have a point. So maybe I think we should define this carefully. So I think I will define it as NC divided by N1 times N2. Okay, so if this is also N, this is also N, then I will have N square here. This is N. So or the other way. N1, N2 by NC.
We can multiply it by 2.
But we have to, okay, you can multiply that by 2, or let me just see this, N1, N2 by NC. No, then you have 0 problem. Okay, right now I think you can just say that we can multiply this by 2. 2 times NC, so this is 2N and 2N. Okay, otherwise, okay, this is fine, right? If I multiply this by 2 times NC by N1 plus N2, then I will get A1, I will get A2. I exactly don't remember what was the way they have defined it, but it doesn't matter. So if I define it like this, I will get A is equal to 1 for wave nature and A equal to 0 for particle nature.
Sir, I have a doubt here, sir. Sir, when this coincident detector clicks, what about this D1, D2? They will function or they will remain idle?
No, see, when D1 and D2 are clicking simultaneously, then coincident detector will click. So first D1 and D2 will click, then coincident detector will click. So it is like after D1 and D2 are clicked simultaneously, a signal will come, and then coincident detector will register a click.
Oh, it is after that.
After that. Okay.
Sir?
Yeah.
But in another experiment, when means both the detector means normally it will be either D1 or D2 will click, no? After passing through a beam splitter, even if we are sending one photon, so that time it will click only when one of the detector will click. It's not like simultaneously click.
Yeah, so that is what we have observed when we did that first experiment with the beam splitter, right?
It should be 0, sir, then.
So it should be 0.
Yeah.
Okay,
Means D1
so
not click simultaneously.
yeah, so at that time we felt that it should be 0, but then after we looked at the interference effect, that means we were able to predict that it will go to D1, it will not go to D2. Such a thing will happen only if you have wave nature.
No, but that is because means after getting reflected, if we consider the state of photon is changing, the reflected and transmitted photons are different states.
Okay, so you are saying that something is happening at the second beam splitter. As far as second beam splitter is not there, it should
what
be.
Means after passing through the first beam splitter itself, the transmitted photon and reflected photons, they have different states. They have different phase.
Okay, that is fine, but my question is there something like transmitted photon and reflected photon?
Okay. That is a question.
Or is there a photon that is transmitted and reflected? That is the question. Just like cat live and dead.
Dead, yeah. Okay, sir.
Okay, that is the question. That is the question. So if you say that there is a photon that is both transmitted and reflected, that can happen only if we think of a wave nature. Okay, so a photon is either transmitted or reflected, or it is transmitted and reflected. If it is transmitted and reflected, A will be equal to 1. If it is transmitted or reflected, A will be equal to 0. Is that clear?
Yes, sir.
Okay.
So in this case, I think that NC by N1 plus N2 is correct, because NC means it is a number of coincidence, and N1 plus N2 should be equal to NC. So I think NC by N1 N2 is N plus 1 2 is correct, I think.
No, the only point is that I'm just looking at this. Suppose if you say that you have D1, D2, and let's say it's a wave nature. Wave nature means all the photons will come to both detectors, right? And then coincident detector also will register n clicks. So if I write nc is equal to n, n1 is equal to n, and n2 is also equal to n, which means my nc by n1 plus n2 is equal to half. So just to make that one, I am multiplying with this 2.
Okay.
Okay, so then this will be equal to 1.
Sir, you can write directly as NC by n, right? Like only n.
Yes, I can write like that.
Yeah.
But then I'm just defining it in this way so that we can make a case for if n1 and n2 are not equal. Okay, in some other experiment, maybe we can think of keeping n1 and n2 different. Then this formula will also be useful there. Okay, so I think even then it is fine. Okay, so at this point, even if you write down nc, okay, nc by n, even if you write this, then also it is fine. I think what you said is correct. Okay, for our purpose, I think let us even define it as nc by n. Okay, so that is fine. Okay.
Sir, I think 0 will be equal to 0 will be the answer, sir.
Okay, 0 will be the answer. Okay, so but I can say that some of you may have some reason to say one answer or the other. Some of you have some gut feeling saying this should be this or this should be that. But I am sure every one of you are curious to know what the answer is. Isn't it?
Yes, sir. Yes, sir.
Yes, sir.
So quantum mechanics has got this very nice feature that it always keeps you on toes. That means you would be expecting, okay, this is what it is, that is what it is, like that. Okay, and let me tell you that the experimental result is actually something close to 2 or something like that. Is it understandable? Why there is a
Sir,
silence?
it violates the conservation law.
Violates what?
Conservation of particles.
That means you have detected more than what you have sent.
Yeah.
I agree.
Sir, A is defined that way, what you have said, 2 NC by n1 plus n.
Yeah, let's say NC by n, just NC by n.
Okay.
Okay, so let's see, experiments are always, I mean, they are like gold standards, right? So experiment is giving you some number, it cannot be wrong. What can be wrong is only what you thought you understood it.
Sir, the coincident detector is like a correlation, no, sir?
No, coincident detection is exactly like what I said. If both are detected, both are clicking, this will click.
So it is like correlation, no, sir?
Yeah, it is correlation between the two measurements.
So the correlation, can it be like 2?
That is what experiment is giving.
Okay.
Okay.
Same thing, sir, what Devanjan is saying, sir. One photon means we have accountability at the source level, right, sir? We are sending n photon. So
yes,
there must be 1-to-1 correlation. 1 photon, 1 click. But how to, sir?
So that's quite intriguing, actually. I'm not, imagine what people would have thought. See, quantum mechanics was known from 1925-26 onwards. We know Schrodinger equation, Dirac equation. People have worked on quantum mechanics, and then finally they do this experiment and then get this result. Okay, how many people would have been sleepless for years together? Okay, so this particular experiment was roughly done, as I told you, in 1956. Okay, but this result, which is extremely surprising result, was explained only in 1982 or something like that. So roughly something like 30 years, 25 to 26 years of struggle by best of the brains in the field to understand this. And the correct understanding of this one is related to a proper understanding of the state of the system. So people understood after 30 years of struggle that we didn't understand the state properly. Okay, so I do not want you to make this kind of a mistake. So we will try to understand the state properly. And if you want to know how do we understand this, you have to understand state properly. And I will not be able to tell you or give you the answer now. But if you follow this course and you understand the state and things like that, then I think you will be able to get this. So if you are excited or if you are intrigued by this result, please continue attending the course. So this is some kind of an advertisement for the course. Okay, so now the question that I have, so this experiment was not very decisive. So let us come back to this question. So I have a source and I have a beam splitter, and then I have a detector D1 and I have a detector D2. And so the two questions that we have raised: photon after beam splitter. Okay, so this is our beam splitter. Photon after beam splitter is transmitted or reflected. This is one possibility. Okay, so this is possibility 1, is transmitted and reflected. This is possibility 2. Okay, now we have to decide which one of these two is correct. In the previous experiment, we hoped to decide, but it did not, it gave us some new problem. Okay, so now how do we decide this? What is the result that I have? Experimental result. Experimental result is that send n photons you send, then n by 2 are at D1 and n by 2 are at D2. Okay, so this is the kind of result. Now a given photon is either at D1 or at D2. Now this observation, is this sufficient to choose one of these two options? Okay, so please understand that. So let me also tell you why I am saying that it is coming to D1 and not D2. That means this argument that I am giving is actually equivalent to saying A is equal to 0. Correct? A is equal to 0. Now you may say that, okay, we did not find A is equal to 0, but as I told you, in 81, 80, 82, 86, like that, there were experiments where they have understood about the state and properly done the experiments. Then they found A is equal to 0. So that means I am actually assuming some of the knowledge in late 80s present to us. So photon, ultimately people showed that A is equal to 0 is the correct answer, which means that a given photon either comes at D1 or comes at D2. Okay, so this is an experimental result. Now, if it comes at D1 and D2, this experimental observation, is it sufficient to choose this one or this one? That is the question.
Sir, can you ask the question once more, sir? Like, I am a little confused.
Yeah, the question is that when a photon comes from a source, a single photon, and crosses the beam splitter, okay, now it is either transmitted or reflected at the beam splitter. Maybe it takes the decision randomly. You will not be able to predict it, but it is either transmitted or reflected. That is one option. That is my one. This roll number Roman 1 is that option. Other thing is this photon which comes to beam splitter is transmitted and reflected. It's not either or. This is second option. Now, among these two options, which one is correct based on the observations that a given photon will come only to D1 or D2?
So one, sir, option 1.
Option 1. Why?
Because it's coming either at D1 or D2, so we cannot divide a photon. So it is either transmitted or reflected. If it is both reflected and transmitted, then we can divide the photon. That is not possible.
Sir, but the previous result showed that it should be 2, right? Previous experiment.
No, forget about that result. Okay, that result came because people did not understand the state properly. And then in 80s, it was corrected, and then people understood that this result is correct. Okay, it will come either at D1 or at D2.
Okay, sir.
Sir.
Sir,
if it is reflected, that transmitted
then obviously
by...
it should be 1.
Sitikanta, what are you saying?
Sir, that evanescent is that transmitted part, sir?
So first of all, we don't know that it is a wave, right? So we are saying that it is coming to either D1 and D1 or D2, not both. If it is a wave, then we would have both, right?
Yes, sir. Yes, sir.
Now, I want you to understand one thing, that in this whole set, in this whole scheme, where is the measurement being done?
Detectors. Yes.
There is no measure. Only at detectors we have measurement.
Yes, at detectors we have measurement. So if at all some selection has to take place, where the selection has to take place?
Beam splitter.
No.
Detector
Beam
level,
splitter, it's going to take place at detector level, right? So even if it is both transmitted and reflected, okay, even if it is both transmitted and reflected, when D1 is measuring it, it will only show one of them, right? Transmitted or reflected. So now it is like this D1 and D2 are going to, so D1 is going to detect transmitted and D2 is going to detect reflected. That they are detecting, does it mean that before it is coming to detector, it was either T or R, or it could be T and R also?
But
sir, at the beam
detector
splitter
is
only it should decide, right?
Sir,
why should it decide? Why should we decide at beam splitter?
Sir, one question, sir.
Hmm.
Detector is just a photon detector, right? It won't detect it is a transmitted or reflected. It's not like that, right?
Yeah, that's fine.
Yeah, then it will detect all, like if the D1 is detecting only transmitted means, then whatever you are saying is correct. Like it will detect because in beam splitter it won't decide like is it a transmitted or reflected, because after if you put in place of D1, if you put one more beam splitter, you will get two rays, one transmitted and reflected.
Yeah.
Yeah, that means after the first beam splitter, you have both transmitted and both component you will have.
Okay.
Then if you take D1 as only photon detector, like without distinguishing the transmitted or reflected, if you take like that, then
so there is no transmission and reflection is not going to change the photon. It's a photon. It's a transmitted photon or a reflected photon.
Yeah.
Right.
Yeah.
So it's a photon, and photon detector will detect the photon.
Sir?
Yeah.
Sir, here detection is like collapse, no selection you said, right? So before detection means it can be superposition, right? Reflection, or if we extend that state idea, because we are not doing anything to the photon. Like here also we can write it as superposition of reflection and transmission, and at D1 before D1 also we can write.
So can we write like the photon as some 1/√2 R state plus 1/√2 T state, and at the detector the measurement is happening, so it will collapse to one state like that.
So that means whatever 2 that we are writing here is what should be correct, right?
Sir, I have a doubt, sir. Sir, means if we remove the beam splitter, the D1 will only detect, right?
Correct.
So if we put the beam splitter again, it will either be D1 or D2.
Correct.
So at D1, at the beam splitter only, the photon decide it should go to D1 or D2, right?
So that is what your understanding is. That's what your thinking should happen. Okay. So what actually happens there? Does it care about what we think should happen? It need not, right? So we are trying to understand how to improve our quantum thinking such that we appreciate what happens. Okay. Now I just want you to think.
I'm thinking.
I just want you to think about this problem together with this one. So I have a source, I have a beam splitter, then I have a mirror, and I have another mirror, and I have another beam splitter. So D1, D2. So what did we observe? If you send n photons, all of them will come here and nothing comes here. This is what we observed. Beam splitter 1 and beam splitter 2.
I have a doubt, sir. Can we write a photon state as reflection and transmission, the component of reflection and transmission as a photon state? No, right?
That is precisely what I'm asking. If you can write.
No, we cannot write. It won't have Hermitian operator, right? Like if you have a Hermitian operator, then you can take the basis of Hermitian operator and write as a superposition of any state.
See, to write a state, we don't have to have any Hermitian operator, right?
I mean, no. I mean, if I want to measure some quantity.
Measuring is different.
Yeah.
measuring is different. So see, you are saying that in the detector, what are you saying? You are actually measuring number of photons, right? So you may have some number operator, and number operator will be Hermitian operator, and so on.
Yeah.
Okay. So, but for writing a state, I don't have to worry about whether it is it corresponds to some eigenstate of some Hermitian operator. State is arbitrary.
Sir, if reflection and transmission I consider as the eigenvalues, with them this reflection state and transmission state are the two basis state eigenstates. That we can think.
Yeah. So now the point that what I think Sharath is saying is that what does that physically mean? Reflection, transmission, what kind of Hermitian operator does it correspond to?
Yeah,
so that
exactly.
is that's what he's asking. But what I'm saying is these are like abstract notions. Now my question here is that what is happening at the beam splitter? Can we consider that as a Schrodinger cat-like state? We don't know whether it is transmitted or reflected. It is we have to keep that as some alpha times transmitted plus beta times reflected, and we will know only when a detector is interacting with this system. Till that time we don't know. Just like when we open the box only, we will see whether the cat is dead or alive. Till that time we are ignorant, and hence.
Sir, but if even at D2, if it detects, like even the detector detects the photon, but it won't tell it is a transmitted or reflection, right?
No, that is our language only.
Okay,
if D1 is detecting, we will call it transmitted. If D2 is detecting, we will call it reflected.
But if you put one more beam splitter, you will get one more reflection and transmission, right?
Correct. That is why. So essentially, what I'm trying to
means what I mean is, like, if you measure something, then it collapses to that state. That means you have that the state of the system is it will be in that state.
Yes.
But here we are not measuring any reflection or transmission.
Correct.
Yeah.
Reflection or transmission. I'm just saying R and T. I could have simply said that this is X direction and this is Y direction. Right. So I could have simply said like this: if a photon is coming in the Y direction, it will be detected at Y2. So this is just a name. Reflection or transmission is a name. And a photon does not encode any character called transmitted one or reflected one. That is what we have seen by putting two more beam splitters here, right?
Yeah, exactly.
N by 4 we get. So it doesn't have any encoding of this transmittedness or reflectedness in this. It's just a label.
So, sir, so until we measure, it can have both the state.
So is there any solid reason to believe that it is like that?
Sir, the photon number state is a qubit, no sir? Like if it is a single photon state, then it's 1, gate 1, and if it's a vacuum state, then it's 0. So at detector, we are getting like we are detecting it is actually we are getting a projection. If it's if photon is detected, then we are getting a projection in the single photon state, sir.
Correct.
So that is like a Hermitian operator.
Yeah, that number operator can is a Hermitian operator.
The Fock states. So
yes.
So this is like I think what Sharath is asking.
No. So, yeah. His question was with respect to reflection and transmission, that properties. But now I think he understood that these are just labels.
Then I got confused, sir. If then what does this beam splitter does? Because it just re-express in two directions, X and Y. The state was.
Yeah. So basically, it is like a photon was coming in the X direction. And after beam splitter, it will go in X and Y directions. Can we conclude that?
Sir, in my understanding, beam splitter is a black box within which a demon stays, and a photon comes and demon tosses a coin. If it gets hit, then it transmits it, and if it gets reflected, if it gets zero, then it sends in the reflected direction.
Yeah. If that is so, then this result, can we understand this result? So let us say
0 and n. 0 and n.
0 and n. So suppose let us say it is transmitted, then it will be either transmitted or reflected here. No, the same demon will sit here and toss a coin again. Then I should get n by 2, n by 2.
Yes, sir. Yes, sir.
So I am not getting n by 2, n by 2.
Yes, sir. So, sir, it's a capital mistake to theorize before one has data, because experiments give us data, and we are trying to a priori guess the answer. We are trying to theorize before we have that experimental data. So
Correct.
there we are committing the capital mistake.
What is a capital mistake?
Sir, it's a quote of Sherlock Holmes, sir. It's a capital mistake to theorize before one has data.
No, now we have some sufficient data, right? See, if you we have these experiments, and we have to say something about. See, what is my question? My question is only this: is 1 correct or 2 correct? What is the correct way to understand? Photon after beam splitter is TRR, or you can, if you don't want TRR, you can say X or Y, or X and Y.
Sir, sir, like when we solve this Schrodinger equation, sir, that we get the state at a different time. Means evolution we get, but the probability and all will remain same. So,
No,
sir,
no,
means that normalization of the state remains same, preserved, right?
Yes, that is correct.
So here initially it was coming along X. After that it changed to X and Y. There is like a rotation. So is it like same, sir, evolution, or I don't know how to phrase.
So basically what I'm trying to say is there are two issues. So let's try to see how do we understand this picture. Okay. Now let's say that I have the state after S and before BS is, let's call this as X. Okay, because it is moving in the X direction. Now after BS, okay, what is the state? The state will be X from our understanding of how do we write states. So 1 by root 2 times X plus 1 by root 2 times Y. Okay, I don't know whether this is the state, but let me just write it, because
Sir,
yes.
This I factor will not come because of the reflection. So 5 by 2 page.
Yeah. So that is why I put a question mark. I want to argue.
Okay, sir.
I want to see whether what I am writing in what way is incorrect. Okay, so now what happens? So you have this M1 here and M2 here. So what M1 does? M1 will change X to Y. M2 will change Y to X, right? So after M1, M2, this will be 1 by root 2 times Y plus 1 by root 2 times X. Okay, so I have to put the same question mark here also. Now what happens at after BS2? After BS2, what do you think will happen? BS1 and BS2 are not same, no? They are same. Okay, this is after BS1. So after BS2, what happens? 1 by root 2 into this y will become x and y again. So 1 by root 2 into x plus 1 by root 2 into y plus 1 by root 2 into x also will become 1 by root 2 into x plus 1 by root 2 into y. Okay, so this is what it is. Now we can ask a question. What will be the, so now you have what? 1 by root 2, 1 by root 2. So you have something like x plus y. Okay, so because we have x plus y, D1 will detect x. That is, if D1 is, so you are now calling a detection, right? So if measurement collapses this to selects x, D1 will click. If it selects y, D2 will click. Correct. So selection will happen at the time of measurement. So it will be either x or y will be selected. So D1 and D2, both of them will click. And there is a this equal coefficient is there. So you should get n by 2 photons. This is what we are getting. But that is not what is experimentally observed. Okay, that is not what is experimentally observed. So we go back and then ask and realize that, okay, now I want to get experimentally observed result. So I realize that quantum states have to be complex vectors. So that means I can actually think of coefficients which are complex numbers. Then you realize that, okay, this is going to, this transmission is going in the x direction, this is going to y direction, but it is not merely changing it into y, but it is adding kind of a phase. So let us say I will put an I here. Okay. So if I put an I here, then what happens? This becomes, so maybe I think I should just write with a different color. Okay, so let me say that I will put an I here. Then this I will become I here. Now one has to be very careful here. So there is an I sitting here, and the Y that is coming from here, the Y that is coming from here, when it is transmitted, Y will be going in this direction. Okay, there's 1 by root 2. So Y will be going in this direction, but then X will have an I here. Okay, whereas when the X is coming like this, X will not have this, but I will have this. Okay, so now you go back and then look at what is the, so let us now from here write down this one. So this is I by 2 x plus 1 by 2 y, and here you have plus I by 2 x and minus 1 by 2 y. Okay, so this and this will cancel. So you have I times x. That means what? There is no y. So D2 will never click. Only D1 will click always. Follow? So this will tell me what a beam splitter is. So beam splitter is kind of a unitary operator, which I can write it as a matrix in this fashion. Okay, what is this matrix? 1. So what? So you may say that, okay, this X, I can write this as 1, 0, and this Y, I can write it as 0, 1. So now what happens when a beam splitter is acting on this X? You will get X plus I times Y by root 2. So what does that mean? That means this is equal to 1 by root 2 times 1I. That is what this is, right? 1 by root 2 times 1I. So if you are taking 1, 0, you should get 1 by root 2 times 1I. So that means 1, 0, you will get 1, and I must have I. I 0. Of course, one has to be careful because this has to be a unitary operator. Okay, so anyway, let's not worry about this. But you can see that if we have to understand this experimental result, what should beam splitter do? Beam splitter should make this state. Okay, so that means what? If Mach-Zehnder, this is called Mach-Zehnder interferometer. If Mach-Zehnder interference is correct, then this beam splitter acting on this X must make it X plus I times Y by root 2. Exactly like Schrodinger cat is both dead and alive. Okay, so it has both X and Y in the state. Now you go back to this experiment. What happens? Because it has both X and Y, there is a probability that D1 is detected. There is a probability that D2 is detected. And probability of D1 detecting is half. Probability of D2 detecting is half. Okay.
So, sir, now I understood, sir, why it will come one at X only, because it's reversible, right? If it beam splitter, if we put again once again, then since it's reversible, unitary operator is reversible.
Yes.
Yeah,
yes.
Then you will get only one line.
Correct.
Yeah.
So what is kind of a single most important thing that you have understood today? Okay, so this is my last question. If you, Arpita, we have overshot the time anyway, but just one last question. Okay, so so I want you to, I mean, if possible, please try to look at the lecture once again after 1 or 2 days, because what we have discussed today is very, very important and very, very basic and fundamental understanding. And if you understand this, then I think many things in quantum mechanics become easy to appreciate. Okay, I will stop here.
Sir, I think it's like quantum mechanics is complex but real.
So your real is not in terms of real numbers, right? And perhaps complex is not in terms of complexity.
No.
You have combined mathematical and physical statements in one sentence. That's good. I agree with you.
Yes, sir.
Okay, so if there are any quick questions, we can ask. Otherwise, we can close.
So, sir, the transmitted
Thank you, sir.
photon goes like without a phase, and the reflected photon picks up a phase and then travels.
Correct.
So, is it like consistent the Stokes law, like Stokes like condition?
Yes.
So, so the Stokes condition is classical, no, sir. So, why do you need quantum mechanics for this?
No, what I'm saying is that the state description with the beam splitter is different from polarization description that I have given, because these are two different degrees of freedom. Okay, Stokes Jones vector or Stokes parameters are only related to polarization. So you can also talk about Stokes parameters even for a photon. The language is very same. There is no difference between classical language and quantum mechanics language for polarization degree of freedom.
Okay, sir. Okay, sir.
Yeah. Okay, I think people are tired already. So,
Sir,
George,
I feel, sir, more incomplete after this. So many. It's
yeah,
like,
actually, I mean, if
We
you are
need to
feeling,
rewatch it, sir.
if you are feeling incomplete, that means you are in the right direction. See, the real nature of learning is that more you learn, more you feel incomplete.
yes, sir.
So one off-topic question, like just curious, how do you prepare before lecture, like all these things, like.
I don't really spend a lot of time in preparing, but usually what I do is I keep thinking about this all the time.
Okay, okay.
So many of these thoughts are collected over, for example, I finished this class till next Saturday. Several occasions I keep thinking about what I should present. And sometimes if I have to read, then I will read depending on what I require to present. But there is a continuous effort. It's not that before the class I sit down and prepare or something like that.
Okay, sir. Okay, sir.
In Sunday class, one sir told you have to sleep on the problem. Basically, sir is walking, thinking, eating on the problem.
Yeah, sleeping on the problem is not my usage. I think Niels Bohr used to say this whenever he found some problem which is very tough. He says, I have to sleep over it. So sleeping over has a very nice thing, because in history many people have got ideas when they are sleeping. So this is related to some back processing which your mind does even when you are asleep. And this back processing seems to have some power which gives you solutions when you sufficiently think and then sleep. Without thinking, if you sleep, nothing comes.
Yes, sir. That's what it means. When you told me, I thought how much realization is there, and that impact is still there on me.
Yeah. I think it.
So sir, the beam splitter is a combination of the identity operator and a phase gate.
Yes, one can say like that in terms of the gates.
Okay, sir.
So shall I stop the
Yeah,
streaming?
yes,